We expect the numbers on a digital clock to flip with flawless precision at the exact moment a train's automated doors are snapping shut. Waking up, catching a bus, or starting a meeting requires absolute synchronization across a massive, invisible grid. If our clocks drifted by even a few seconds, the macroscopic world of logistics and transport would begin to desynchronize. In professional sports, this synchronization determines history. These omega timing lines capture microscopic gaps between athletes that the human eye cannot perceive. On this scale, a winner is decided not by a full step, but by a thousandth of a second. High-stakes results like this require more than just a fast camera. They require a single universal standard of measurement that every official on Earth agrees to follow. That standard is the International System of Units, or SI. It establishes the second as the universal building block of time, providing a common language for every scientist and timekeeper in the world. This system scales with rigid mathematical certainty. 60 individual seconds form a minute block, stacking into an hour. Science demands specific notation. The symbol for second is a lowercase s, no plurals, no full stops. We write 10s, not 10 sec, ensuring universal clarity. Learning this scientific grammar is the first step towards seeing the machines that actually do the counting, the high-speed oscillators hidden inside our technology. The transition from human time to the electronic world is best seen in an early digital watch like this vintage pulsar. Behind that red glow sits a circuit designed to count faster than any human ever could. Inside, a tiny sliver of quartz crystal is shaped like a musical tuning fork. When electricity from a battery hits the quartz, it vibrates exactly 32,768 times every single second. This constant frequency is the heartbeat of modern timekeeping. A microchip then performs frequency division, a process where an electronic circuit takes a fast signal and reduces it by exactly half over and over again. It divides that 32,768 Hz signal 15 times, until it generates a single steady pulse once per second. This specific mathematical reduction of a crystal's natural vibration drives nearly every smartphone, computer, and digital clock on the planet. However, physical oscillators are vulnerable. Pendulums and quartz crystals physically expand or contract as the temperature changes, causing them to lose their rhythm. To eliminate this drift, scientists moved away from physical objects and began looking at the unchangeable building blocks of matter. This early atomic clock was the first step toward a timekeeper that doesn't rely on gears or crystals. Inside these machines, researchers target a specific cesium atom to observe a hyperfine transition. A hyperfine transition is an extremely stable leap of energy within an atom's nucleus and its electrons. Because this is a quantum property, those electrons vibrate at an exact frequency that never changes, regardless of the environmental temperature or pressure. Humanity has harnessed the laws of physics to create a clock that will not lose a single second, even after running for millions of years. This quantum stability leaves the laboratory to coordinate the satellites in Earth's orbit. Every GPS satellite carries atomic clocks. By measuring the nanosecond differences in how long it takes a signal to reach your phone, the system can triangulate your exact position on a map. On the ground, the global internet requires this same microsecond precision to route data packets across the world. Without these timestamps, the digital traffic moving through undersea cables would collide and fail. Financial markets rely on this absolute timing to execute millions of high-speed trades. Every transaction is timestamped with atomic accuracy to ensure that every buyer and seller is treated fairly across global time zones. The simple ticking of a second on your screen is the visible pulse of this quantum heartbeat, the invisible mechanism synchronizing the navigation, communication, and financial systems that keep our modern world in motion.